Mongolia University to present this.
Hello everyone, my name is Kanghao Zhang and I'm from Mongolia University. I'm presenting our work DBNet, the Dell branch network architecture, processing on spectrum and waveform for single-channel speech enhancement. The other authors are Shulin and Hao and my supervisor Xueliang Zhang. This is the outline on this presentation. We first introduce the task and our motivation. Then we propose our architecture and approaches. The experiment settings and results will be presented in the end. In recent years, single-channel speech enhancement methods based on deep learning have become popular. Its performance surpasses traditional algorithms and shows great potential. The mapping-based training targets in the deep learning method usually choose from magnitude, complex spectrum, or waveform mapping. However, we found that different types of noise may require different types of modeling methods. Our motivation is very easy to understand. As we know, for an impulse-like noise as shown in figure A and B, it is easy to eliminate in the time domain. Only a few samples need to be removed. In the frequency domain, the impulse-like noise pollutes the entire frequency band, and it is difficult to be eliminated by a speech enhancement method based on the frequency domain. In contrast, for a narrowband-like noise as shown in figure C and D, the noise is distributed on the narrowband, and the frequency domain-based method covers well. In the time domain, the noise and the speech are coupled together, and it is hard to decouple by an enhancement method based on time domain. So in this paper, we explore a novel speech enhancement algorithm called DBNet, which combines the time domain and frequency domain together. The overall structure of the proposed method, which called DBNet, is shown above. The DBNet is a double-branch architecture with alternate interconnection. The two branches are responsible for spectrum and waveform modeling, respectively. When the utterance is sent to the network, it is first divided into frames with a window length of 20 milliseconds and a window shift of 10 milliseconds as the input of the time domain branch. Then we use an SRS module to extract the shift real spectrum representation of the speech as the input of the frequency domain branch. Features are downscaled along the encoder, pass through the group LSTM, and then upscale along the decoder. What's new is that we added a bridge layer between the two branches as an interactive module for information in the two domains. Finally, features are reconstructed into clean speech through inverse SRS module and overlap and add module. In our network, we use gated CNN and group LSTM to replace CNN and LSTM. The gated CNN can reduce the vanishing gradient problem for deep architectures by providing a linear path for the gradients. The group LSTM contains two layers of RN, and each layer has two LSTM to learn the features within each group. Between the two layers, a frame-level rearrangement is used to establish the intergroup relationship of features, which guarantees the utilization of intergroup correlation. Then this is the display of the bridge layer. A bridge layer consists of two matrices. Block F represents a matrix which converts time domain information to frequency domain, and block B is the opposite. The size of the matrix is n times n, where n is the dimension of the features in the corresponding layer. Two matrices are both trainable and initialized by FFT parameters, which aims to learn a better conversion method through the network. Finally, we use magnitude-based loss, which is described as Formula 1, where capital S and capital S hat respectively denote STFT of lowercase s and lowercase s hat. T is the number of the time frames, and F is the number of frequency bins. Subscript R and I respectively denote the real and the imaginary part of a complex variable. In the training phase, we use this loss for training on both branches, and we use the output of frequency domain branch as the final result in the testing phase. Next, we introduce our experiment setting. We use WSJ0 SI84 to generate our training and test dataset. For training, 77 speakers of WSJ0 are chosen to generate 320,000 mixtures, along with 100,000 non-speech noise from sound ideas, and 3,000 mixtures in validation set are generated in the same way. The SNR of these utterances are uniformly sampled from -5 dB to 0 dB. For test, two noise, bubble and cafeteria is used, and the rest speakers of WSJ0 are chosen to generate 300 utterances at SNR of -505 dB. The total number of the test set is 1800. As for baselines, we choose CRN, GCRN, and AECN as our baselines. Magnitude, complex spectrum, and waveform are respectively used as the input of these three baselines. We use STOI and PASC as evaluate metrics. At last, we show our result. Table 1 shows the STOI and PASC comparison between the DBNet and the baselines models. It can be seen that the proposed model outperforms all other baselines. Compared with unprocessed mixture, an average improvement of 21% and 1.2 are obtained for STOI and PASC respectively. Based on the above results, we believe that alternate interconnection of the information of two domains can significantly improve the performance of the model and improve parameter utilization. The proposed model was also trained with the DNS challenge wideband dataset. The result is shown in Table 2. It is obviously that the proposed model outperforms the baseline NSNet2 by overall 0.12 score, which means the proposed model can reach great performance in complex noise and reverberation environments. Thank you for listening.
Okay.
Great, thank you for the talk. We'll start with any questions from the audience. Okay. I have one question. I guess you used, I guess, the SNR of -5 to 0 and also -5 to 5 for training, similar to a previous paper. What was the reason? Did you do a sensitivity study that shows that using very low SNRs for training works best?
Oh, using low SNR is for the using low SNR is for the better robustness, and most of our parameters are retained by previous experiments because due to time and equipment, there are not too many comparative experiments. So using low SNR is just for the robustness. And we think low SNR means the more difficult to enhance the speech. So we added this in our experiment.
Okay, great. There's a question online. I can imagine that during inference, you will have different results at two separate branches. How do you get the final results? Which output branch is used?
We use the frequency branch as the final result. We test the result on both branches, but we find the frequency branch have the better performance. So we use the frequency branch as the final result in the testing phase.
Is that better performance measured by DNS MOS or which metric?
We measure it in STOI and PASC and DNS MOS.
Okay. Great. Any other questions? Okay. If not, thank you for the talk. And Harry, can we go on to the next talk?